Okay, hello everybody. We are Team Firebot. We are Blythe, Queenie, Carl, I'm Martha, and we are sponsored by the Washington Department of Natural Resources. Wildfires are burning hotter and longer in Washington state. The suppression costs approximately $153 million annually. There are 2.2 million homes at risk. The Department of Natural Resources is the largest wildfire management team in Washington. Why is surface fuel type data collection needed? When we say surface fuel, it is the vegetation under the canopy. This is what propels fires forward. Fire management teams need the surface fuel data in order to improve their decision-making. The satellite data that we have is lacking when looking locally at landscapes. The current method to collect data is to send personnel into the forest on foot to take notes. And you can see in the bottom right a sample of surface fuel. Our problem statement is, how might we help the Washington Department of Natural Resources streamline surface fuel type data collection to improve decision-making in forest and fire management in the Clay Elm area? Our approach was to ask a lot of questions. Who is the end user for the fuel type data? How do fire management teams use the models? What fuel models how are they determined? What data is needed? How is that collected? And what are the difficulties? This is an example of current models of fuel modeling for fire behavior prediction. Landfire.gov satellite data is used to infer fuelscape, which is used to predict burn probability. We conducted primary research with interviews with subject matter experts, contextual inquiry, and field observations. We had many conversations with DNR personnel. We traveled into the field with them to learn more about surface fuel data. We found that it currently is not being collected because it is too labor-intensive, time-consuming, and expensive. We started to think a little bit about possible solutions: a citizen science app, autonomous ground robot, or drone-based system. We continued our research traveling out to our test site, the Teanaway Community Forest, just north of Clay Elm, Washington. Here's our test site with 20 GPS waypoints that were specified by the DNR for fuel collection. We went and hiked to each waypoint and took photos of the surface fuel, and also a photo to see whether there'd be a potential path for a drone to descend. We hiked for 6 hours, climbing over brush and logs. We came back thinking about the complexity of the problem space. How do we deal with this vast landscape, with the rugged, varied terrain? And how do we move on from hiking through brush with a notebook to look for surface fuel observations, and how do we make a solution that's both autonomous, affordable, and scalable, and has an online database? A little bit of our hiking experience. So we imagined a drone plus a square wave flight plan. Instead of satellite imagery from above, maybe we can design an autonomous drone that can fly over the forest and descend to take photos of surface fuel.
So I'm going to talk about a solution. So we come up with the product of an autonomous drone-based data collection system that streamlines the whole data recording, processing, and storing by providing the user the web interface to let them to initiate and monitor the whole collection process with an autonomous drone. It also provides a database to save data and serve as a data set for future machine learning model training. The reason why we choose this applied strategy of dropping the drone through canopy from the top assembly point instead of having it fly on the canopy all the time is because the path between the GPS point are shorter with fewer obstacles. It could save time, it's feasible in the type environment. Also, it could save computational power and battery without building the map consistently. So our related stakeholders are DNR, fire ecologists, land managers, timber company, and insurance company. We basically have 3 rounds of our user research and testing. For the first one, we are more focused on using the Figma UI plus big autonomous drone to understand the tasks necessary for collecting surface fuel data in the field, reviewing and uploading to the database. The result again is we're able to understand users' workflow through our UI and where we needed to make changes. For the second round, we picked from the Figma to the iOS with the real autonomous drone to better understand our users' interaction as we were designing and building the system. We utilized the rapid iterative testing and evaluation to test a feature. If it's successful, we move on to the next one. So for the final round of our testing, in order to achieve our minimum viable product, we pivot from iOS to the web app with a fully functional autonomous drone system to understand the user's interaction with our product. We utilize the usability testing in the Spring District to let the user to follow the UI to prepare, begin, monitor drone autonomous fly and land the drone. In the end, the users are able to successfully accomplish all the tasks with some minor UI improvement needed. So Penny will talk about the hardware software architecture.
In general, our prototype includes 3 hardware devices. They are a drone, a controller, and a computer. The drone autonomy is realized by having the computer sending a list of commands to the drones. Those commands are relayed by the controller because the connection between the drone and controller is the most stable. At the same time, the computer is pulling the connection status and battery level from the drone every 5 seconds. It is also requesting live video streams in real time through the RTSP protocol. Because the computer is handling many requests at the same time, so we utilize multi-threads to handle the requests so that they won't interfere with each other. We also provide a local web app to the users, which is built upon the Flash framework, and the live video stream is rendered in a window by OpenCV. In addition, user can also request media and metadata from the drone directly. Here's our user experience flow. We have 2 scenarios. In the first scenarios, users can use the user interface and the autonomous drone to do the data collections. The users firstly should create a mission by adding a list of GPS waypoints to the missions. Then they can start data collection process by simply clicking on a button. At this time, a live video stream will pop up and the users can monitor the flight process with it. After the drone returns to where it take off, the user can land it. In our scenario 2, users are allowed to download the data from the drone and review the images. Here are our prototype iterations. In our first iterations, we create low-fi prototype with Figma. Then we develop the drone autonomy, followed by, in the final iterations, we create another web app and integrate the backend with the autonomous drone.
Thank you. With a working functional MVP, we reevaluated our business case to verify whether our solution is a viable product that we can take to market. Our value proposition encompasses a product that is capable of accurately and efficiently collecting field service data that is able to reduce costs, collection times, and potential risks. Our improvements overhaul paper-based collection methodologies and upgrades collection practices to an automated process that implements machine learning attributes. For the future, our sponsor intends on utilizing several aspects of our prototype into their field collection processes, and before we can implement these features, we have to make a couple of improvements to our process, which is outlined in our 6-month roadmap plan, which includes our user interface, image management system, corrections to our in-flight telemetry, and our image management system itself. Our team recently found out that the US Forest System service has also caught wind of our project, and the plausibility of us having a viable product in the future has a reputation as of now. Lastly, with a working MVP that proves our proof of concept, we believe that our project's value proposition is capable of reducing costs, saving time, and for both our project sponsor and anyone in the wildfire management service. Lastly, since we're an outdoor project that flies, we have to do an indoor demo with a video. So in this demo, you can see that the user right here is incorporating all the missions into the user interface itself. And that includes the name, the GPS inputs, and all the data they want to collect in this process. Here we have a chase drone with an overwatch, watching over the drone flying itself, as well as what we see with the user here. So as the user is operating them, it's completely hands-free. They don't have to touch the controller at all unless there's an actual issue with the actual flight system. Once it gets to the designated GPS point, it'll descend up to 5 or 6 feet and take a series of photos for cardinal directions, north, east, west, and south, before it reascends and returns back to the user. So as you can see here, it's gotten to its point, it's taking its first initial photo. In a second, it's going to turn, rotate, and then select another photo before it moves on. This whole process takes about a minute before it reascends up to the next GPS point and flies over the canopy. As you can see here, it's ascending back to the user through an automated process, and it's going to land right in front of the user. And the user themselves can witness where the drone will land and correct if need be. Once it touches down, the user can decide to re-lift off or continue the process. And that is the end of the demo. Lastly, we would like to thank our sponsors, the Department of Natural Resources, for being here, as well as Anna Barros and Chuck Hershey for all their support and all the information they give us, as well as GX Facility, who basically gave us this project, but also helped us figure out how to do this entire project. Aside from that, thank you very much for your time.
Excellent, thank you very much. We especially appreciate the arrow and stick, because it's pretty techy. Questions, comments, feedback on this project?
I'm just curious if the field modeling for the collection of the data, is that like a preventative measure, or like when there is an active wildfire, they're collecting that, maybe not in the actual fire area, but nearby?
No, they're collecting it beforehand. So the whole purpose is to collect these images, analyze the data to see what areas are possible areas that need to be treated in the future, as well as possible areas for actual fires to develop.
And I guess the other one is, I'm not sure what because you guys work in the Tennessee Way, right, or something like that area. How do you deal with very densely wooded areas where there's large canopy that you might not be able to find close areas to send down to take photos of actual undergrowth?
Yeah, that's an excellent question.
So we looked at the functionality of our drone, and the mean error for GPS landing is like 3.4 meters. So we're thinking that there has to be an opening that's maybe double that to use in our planning to improve the chances of the drone being able to safely descend, take photos, and reascend. But that's a good question. How to apply this to more dense forests is certainly something we're going to be thinking about in the future.
Thank you. Any other comments? If not, we'll welcome our next team up. Thank you very much.